All right, welcome back to Fluid Mechanics. This will be homework number 5, Part A. Part A is distributed into 3 different statements. So let's start with the first one. So the first problem statement is asking us to derive the momentum balance equation for flowing systems. So let's scroll down a little bit. So for flowing systems, the momentum balance equation is going to look like this. We know that a force equals a mass times acceleration. And we can simplify this further. D mass times velocity over dt. And this can be simplified as well into d mass times velocity of the system equal f dt plus v in dm n minus v out d out over dt over dt over dt. And this will be our momentum balance equation for a flowing system. So let's move on to problem statement 2. So problem statement 2 is asking to use A1 to derive the external bracing force necessary to maintain stationary a pipe with a 90-degree bend having flow velocity V and constant cross-sectional area A. So let's draw a diagram. And we have um, our stationary pipe here with our 90-degree angle. The cross-sectional area is the same throughout. And we have a flow going in and a flow coming out. And we're going to take a positive y direction going up and a positive x direction going to the right. And this will be our A, in this case, our cross-sectional area. Our absolute value of our velocity equal to Q over A. And to Fx, absolute velocity, times our mass flow rate, which is going to be equal to rho absolute value velocity A. So then we get Fx is equal to negative rho absolute velocity squared times A. It's the force in the x direction. Now we have to do the y direction. So we get 0 equal to Fy minus the absolute value of our velocity times our mass flow rate again, rho absolute value velocity times area. So we end up getting negative rho v squared equal to Fy. So these will be the forces necessary to maintain a pipe with a 90-degree bend having flow velocity v and constant cross-sectional area A. So now we can move on to the third problem statement of the problem using A1 to derive the rocket equation. So let's see, we got 3. So to start this off, we're going to go and draw our diagram. So we have our rocket, and it is blasting off, and it is pretty much throwing material down to boost itself upward. So let's start by writing an equation that represents that. We have m dv over dt plus v dv over dt equal to negative v minus v exhaust d m naught over dt. M naught minus ft plus v minus fc equal to negative v minus ve. dv over dt is equal to v fc m naught fct. M equals m naught minus fct, where m naught is the initial mass of the fueled rocket. And this is equal to fuel plus oxygen. Deriving this equation, we get v to 0 of dv prime equal to t0 of vefc over m naught minus fct dt prime. V equal to vefc over negative fc, natural log of from m naught minus fct and m naught. Then v is equal to v natural log m naught over m naught minus fct. And this is the rocket equation.